Good day. I received some new light sources. Let's see if I can show them to you. They look like this. They say they were 6,000 K, and they have a nice look to them. Look like they're quality made. I did some testing on it, and I'll display the data today. This is the first day of testing on these. They are the first LED that I could find that would broadcast or put out light between 5 and 600 nanometers. I don't know why that's a difficult light to find. However, it did take me some time to find that specific light. So what we see here is an opacity curve and the corrected color shift curve. Now, I'm not sure the correction is proper for this light source. However, it's what I have. I'll do some more testing with this light in a hot box to determine if I should adjust my correction factor. It looks very stable. Opacity's pretty consistent. We have a peak of 40, maybe 58. We have color shift both to the blue and to the red. I'm not really sure. I guess that's to be expected, having a light source with almost equal red, green, and blue indicators, or the levels are. So a 9-hour test, and then I had to reboot my system. That shut the system down. However, very good control of our smoke going out and some very interesting data. Take a look at between 0 and 1 hour, our opacity actually goes negative just a little bit right after the peak of the fire. Now, this fire went very quickly. I got it started and it took off fast. So I'll go through my charts here and we'll see just how good this light is. This is the first hour of data. We have presented opacity, our color shift, which would be normal, our corrected color shift, which is the yellow. The green line is the sensor temperature that's on the light receiving sensor. What we can see here is that I got the fire started. We had a 40% opacity for a brief period of time. This graph is 1 hour, from 0 to 1 hour. So at roughly a tenth of an hour, 6 minutes or so, we have a 40%, and it drops down to 20. And then by the time we get to 0.2 hours, we're down around 0 opacity. Then around 0.3 to 0.4, we go negative opacity, and we see that on occasion, not very much. This is only like 3 to 5% there, and then it hangs around just over like a 3 to 5 positive opacity, and the color shift kind of follows along with it, running quite well. So the corrected color shift actually goes below the line, so that's why I'm thinking we have to redo the calibration of the color shift for the light source that we're using. But a good graph with some interesting data. We see a lot of color shift to the red between 0.1 and 0.2, and then extending down to 0.3 hours. And then it just rides along with the opacity out to the end of the hour. Good data. We'll move on to the next. This chart is our peak wavelength, and it starts off at roughly 580. We see a shift to the red and then a shift to the blue. Then it just kind of rides along for a while. I put another piece of log on right at 3 hours, and we get a small color shift to the red out to 5 hours, or just before 5 hours, and we get a couple of peaks to the red, and then it just runs out for the next 9 hours, not much happening. So very interesting data. You can pretty much tell when I put significant fuel on. Also, here we are. When in the first 1/10 of an hour, it goes positive and then it goes negative. That's, in 1 hour. That's 1 hour. In the first hour, we're warming up the stove very quickly, and it goes red, and then it goes blue. Just a little bit. That's very interesting data. This chart is the actual diode responses. We see that the clear is pretty much the red, green, and blue added up. And the red, green, and blue are all coming in at just under 20,000 counts. The clear is coming in just under 50,000 counts. So I've adjusted this light correctly in my mind. I don't like to see clear over 50,000 because it takes the sensor and puts it into a different gain mode. So I'm trying to keep everything within the same gain mode on the sensor. But you can see also the 3 times that I put wood on this fire, and it's clearly in the data there. It's interesting to me that red, green, and blue are very similar. This is a green light. This is, it looks white, but it's right there at 550. So it's almost equally red, green, and blue in color. So I'm calculating my normalized a little differently. I used to use percent of max. However, I'm using change from the initial reading now. So I have that listed as percent change on the key there. What you see here is how the light sensors differ in their response to what's coming through the light. So it's they're working together pretty well. We see the one indication where we get brighter light. That's at about a half an hour, or 0.3 or so. We see where blue is scattered a little bit at the peaks of the peak drops there. But everything's riding together pretty well. There's not a big difference in the values throughout the test. So this is a good light. It's well balanced and it'll give us good data. And so I'm enjoying this data set. This is the first data set with this light. This is my rate of rise chart. And a couple things I can tell you here. This thing really took off. We went up to 35 degrees per minute right off the bat. Evidently, I started my fire right, or the algorithm I use to control my combustion air fan is dialed in. We can see that it crosses zero again at about 1 hour. Occasionally, this term comes up called soft heat, and it's a difficult thing to understand. However, wherever this line crosses below zero, you're essentially giving soft heat. The stove is giving soft heat. It's not making enough heat to gain in temperature. It's losing it to the environment. This is what they're referring to with soft heat, and wood stoves put off great soft heat. So as the stove cools down, soft heat. This is my data acquisition system, thermocouples, looking at 3 key indicators. The yellow line is the heating air coming off the stove. So if anytime that's over 100 degrees, it's putting out good hot air. So we got a good 9 hours, 8 to 9 hours of heat off this stove. And we only put fuel on like 3 times. So that really good heating out of the stove, due in part to my control system and the dry fuel that I use. A couple of indicators on this chart. We got almost to 500 degrees before 1 hour. And that was a testament to the my fire building skills. A couple of things in the red line or the orange line is the stat gases, and you can pretty much see every time I open the door. I open the door sometimes to disturb the fuel. I open the door to put new fuel in, and you can pretty much see where I open the door to do something. Every time there's a drop in temperature. So I see 1, 2, 3, 4, and 5 times that would be considered a drop, and I open the door to do something. The last one being at 6 hours, the first one being just after 1 hour. Of course, when I started the stove, I had the door open. This is my control system fan voltage. I work with the algorithms to try to figure out the best airflow for the wood stove, considering how much smoke it's putting out. So it'll go into different modes depending on how much smoke is being released from the chimney or how much smoke we measure. And we have a limit of about 10 volts on the system. That's a 12-volt fan. It can easily handle 10 volts. It's not running at the optimum. However, you don't get much more out of the fan from 10 to 12 volts. You can see that it's constantly cycling up and down, and that's what makes the pretty flames that we see. I don't know what else to say other than I needed to see what this fan was doing, and so I made this graph for myself. I'm sharing it. If I turn it off and do a transition here, this is the flames that I like to see. I like good luminous diffusion flames, and I've prepared an algorithm that almost always produces these flames. And this is somewhat proof of concept, or you can see by the flames that I'm controlling it so that there are flames all the time. And this one, I think I've slowed it down a little bit and colorized it a little bit. It's still a beautiful fire. Thanks for watching.